All right, how's everybody doing? Professor Brown again, back with Workout Wednesday. Specifically today, we're going to be talking acid base, and we're going to be talking about calculating pH using KB. So calculating pH using KB. We all at this point should be very familiar with the equilibrium constant reference material. You will be provided this for all assessments, quizzes, and exams. And this is telling us Ka, which tells us the strength of an acid, weak acids for the most part on this, and the strength of a given base. So there are other videos involved with calculating pH from Ka. So now we're going to calculate pH from Kb. So let's take a look and use ethylamine. So we're going to be using ethylamine, which is a nitrogen base, and it has a Kb value listed. So the question that I want to ask is something along the lines of, can you determine pH of a, let's say, 0.03 molar solution of C2H5NH2? Okay, so we're dealing with ethylamine, and as soon as you see determine the pH and you have concentration, know that you are going to be dealing with an ice table situation. You're going to be dealing with an ice table situation, and from there you're going to be able to determine amount dissociated, and then from there determine concentration of an acid or a base in solution. Okay, now if we want to talk a little bit of theory, if you take a look at ethylamine structurally, and this is just to get more familiar with why is it in fact a base, not just that it is. Ethylamine looks like this, and the basic portion of the molecule is this lone pair here, right? And we should remember from our molecular geometry in Gen Chem 1 that this is trigonal pyramidal, and this electron pair out here, when it interacts with water, it plucks a hydrogen, creating something that looks like this, right? Okay, and all I did here was show you this is the rest of the molecule. I just didn't redraw it. So this is what occurs when water is involved. So we end up with H2O over here, and then over here we end up with OH. So in solution, this is kind of what happens. Now when we draw this and write out our reaction, as we should always get in the habit of doing, plus water gives us C2H5NH3 plus hydroxide, and we go to an ice table. Now, do not get in the habit of always working with acids or always working with bases. You want to be comfortable with both. Okay, so we've been given the initial concentration of our base. In this case, you can go ahead and label it Ba, conjugate acid, conjugate base. We know we're never dealing with water, and we got 0 initial for each of these, and we're dealing with a plus x, x, minus x, 0.03 minus x. Okay, so again, being able to fill this table out with ease and making sure you're not making any mistakes is imperative for this chapter. Now, to get pH, OH minus will give us insight into that. It won't give us pH directly, but it will be able to give us information that we can calculate pH from. So we now have to use the Kb. So the Kb off of our reference material is 4.7 times 10 to the negative 4. Therefore, if we remember that our Kb expression is equal to products C2H5NH3 plus concentration of the two products, in this case, all over the original base, H5NH2. We can plug these values in. These values are effectively Kb equal to x squared over 0.03 minus x. And remember, we said that we can drop x in scenarios where Kb is, if 0.03 divided by Kb is over 500. So 0.03 divided by 4.7 e to the negative 4. It is not, right? It is not. So because of that, we need to keep x. And we're dealing with 4.7 times 10 to the negative 4 all over 0.03 minus 4.7 times 10 to the negative 4. Excuse me. We cannot drop x. Let's not plug that in. We have to solve for x. I apologize. I was using the incorrect information. So from here, we do need, however, to make KB equal to x squared over 0.03 minus x. But instead of dropping x, we need to use the quadratic in this case. And I always do that via calculator. And I plug that in here. I'll show you how I do that. 0 is equal to x squared over 0.003 minus x subtracted by the KB value, 4.7 e to negative 4. Notice what I've done here. I've set this up to where I have input this part of the equation into my graphing calculator. Now, if you're not using a graphing calculator, then quadratic equation works just fine. But if you are, here's another example. Using the graphing calculator, set y1 equal to 0, set your y2 equal to this value. Once you go to graph, it will graph a curve for you. Once it is done graphing, you can go second calc 5 and 3 enters, and you will get a value which is the intersection, which is x, 0.00353. 0.00353. So x is equal to 0.00353. And x is equal to hydroxide ion concentration. And therefore, if we know the hydroxide ion concentration is equal to 3.53 times 10 to the negative 3 molar, we can then determine pOH by taking the negative log of this value, 3.53 times 10 to the negative 3 molar. Now, a lot of people are going to make a mistake and take the negative log of this value and report that as pH. This is pOH because we're dealing with hydroxide. So once we do that math, we get a pOH value of 2.45. Now, this is not the pH. We're dealing with a base. We said that, so we should expect a pH that is above 7. And therefore, pH is equal to 14 minus pOH, which is equal to 14 minus 2.45, which is equal to 11.55. Therefore, we are dealing with a basic solution at 11.55 based upon the concentration of ethylamine of 0.03. So this is how to use KB to determine pH. You have to be able to do this, solving for the x quadratic, determining whether you need to drop it or not, and then using the ICE table. Okay, again, if you have any questions, feel free to leave a comment or send me an email.